we're wrapping up acid-base work, and we started talking about titrations, and much of the stuff that we've talked about up to this point is basically to get you to think about what is happening in solution when you mix an acid and a base together. Sometimes there's neutralization, sometimes there's a buffer, sometimes there's partial neutralization. All of these factors together control what's going on in solution. So we often have to think about reactions in parts. It's not just a reaction. It's a reaction and then what happens afterwards. Again, so this is a standard chemistry phenomena. And additionally, what's in solution at a given moment varies depending on the conditions we're using. Okay? And so there are 4 regions in titration. Perfect examples of titration. You're adding a base to an acid, or an acid to a base. And depending on where you are in the titration, the solution matters. Like at the beginning, right there at the bottom, you just have a weak acid or weak base. All right. So at the very start, it is just a weak acid or a weak base. And so it's exactly the same problem as what is the concentration of acid in a, or what is the pH of a weak acid solution. And so that's how we could approach it. The other major point in this is the equivalence point. Right? We can use Chem 1 ideas. You know, we know from the moles of acid, and at the equivalence point, it will equal the moles of added base. But in a weak acid solution, when you have something like acetic acid being neutralized, when you neutralize this, the moles of added base, whatever base that you add, is really soaking up this H3O+, because this is our Arrhenius definition, OH-. So these cancel one another out, and then the system responds by shifting the reaction this way. At the equivalence point, there's no more acid left. And so all we have is this weak acid amount. That's Chem 1. But what we've seen is that if you just dissolve this in solution, it will reattain equilibrium. This is a conjugate base. At the equivalence point, if we started with a weak acid, it is also now the conjugate, the weak base, or the weak acid. That is the conjugate of this. So this equivalence point is very important in terms of, it's very easily to calculate. We can calculate that using chemistry 1 skills. If you know that you have a 0.1 molar solution of acid, and it's 25 mils, and you have a 0.1 molar solution of base, you can predict that after 25 mils of added base, then you're done. All right? At that point, that would be the equivalence point. Now, after the equivalence point, what happens if you add more than the equivalence point? Well, that's turns out that's just a weak acid. That's a strong acid, strong base. So if you had 25 mils of base and 30 mils of HCl, it doesn't matter what the base is, it's a base. And these had both the same concentration. You would neutralize most of the base and most of the acid. So you dump in the HCl, you dump in the HCl, dump in the HCl, and then at some point all the base is gone, and you will have used up 25 mils of acid used. Leaving us with about 5 mils of acid left over that is now diluted into this big mixture. So if you remember in our titration, we had this. All right, we're adding the acid and then slowly, or base, to this titration mixture, drip, 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 drip. And then at some point, you know, the pH suddenly jumps. Well, that's because now there's a ton of base, or in this case, acid. pH would go down. There's a bunch of extra now, and so this extra is just being diluted in there. So whatever our original final volume is, we would just do a dilution. This 5 mils of acid at its concentration diluted to the new volume. Again, that's a pretty standard Chem 1 problem. Neutralize, look at how much acid is left over, and go. Again, the equivalence point is important here. If we know that the equivalence point is 25 mils, because it was 25 mils of base, then we can use that to predict how much extra is left over. So when you see a mixture of an acid and a base, check if how much of each is present, and that's very helpful. And lastly, we have the region between the starting and the equivalence point, and that's a buffer. And it's a buffer through partial neutralization. So in this buffer region, again, we'll use our... now, the buffer is only present when it is a weak acid or a weak base being titrated with a strong acid or a strong base. But mostly that's what we're going to see. And again, buffers are ubiquitous. They are everywhere in the body. And so one of the things we want to think about is the pH effect of behaviors of things. So let's go back to our standard vinegar, HOAC, in water. If you started with 10 moles of HOAC, and you start adding base, and you're adding sodium hydroxide, you're going to add a little bit of sodium hydroxide. It's going to chew up the H3O+. You're going to add a little bit of sodium hydroxide, and it's going to chew up the H3O+, causing this to go down, shifting the reaction this way. And if you added 1 mole of NaOH, it would use up 1 mole of H3O+, chew that up, and in the process it would use up 1 mole of HOAC, and making 1 mole of OAC minus. It would use up the acid and make base. That's what happens. It neutralizes it. And so this process happens whenever you add an external base to a weak acid solution. And so this is our titration. So we titrate, titrate, titrate. At the end, we'll have this nothing but a weak acid solution. This will be there in minuscule amounts. Hence, we can use the weak acid assumption or weak base assumption. But first, we do the neutralization. And so this is what happens. But during this process, the volume changes. The amounts change of acid and base. But we don't have to use moles because of the Henderson-Hasselbalch equation. pH is equal to pKa of the weak acid plus the log of the conjugate base over the conjugate acid. We could plug these values in and solve, would just be fine. But we can also use another trick, and that is fraction towards the end point. So if you think about it, if this was a solution that had 25 mils of acid, and we knew that the end point was 25 mils. Okay, so we're going to say 25 mils. We're going to assume that the volumes are the same. If I were to add 5 mils of sodium hydroxide, that was the right concentration, we would leave us with 20 mils of unneutralized acid and 5 mils of acetic acid, acetate. All of the base added becomes acetate. I mean, conceptually. You can do this with moles. You can take the volume, convert it into moles via the molarity, and then you could subtract out the amount consumed, and you would get this same ratio, right? 5 to 20. And because this is a ratio, you can use that in these equations. The special point is when you have 10 mils added, sorry, in this case it would be 12 and a half, 12.5 mils. In this case, there would be 12.5 mils of acetate. this value drops out, and that would be the half equivalence point in our titration curve. So we did this in class. This was 25 mils. At the half equivalence point, the reason these are equal, well, the reason this works is when these are equal, this drops out and becomes equal to pKa. And so you can use that to find these. So pretty straightforward process when you deal with these. So let's take a look at a problem. So here's a pH. Calculate the pH of a titration with 50 mils of 0.1 molar acetic acid by 0.2 molar sodium hydroxide. All right. So what happens after 10 mils of base? What happens after 25 mils of base? And what happens after 35 mils of base? All right. So we have a 50 mils of weak acid. That is 0.120 molar, and then we have base being added, that's 0.240 mole. All right, what's the equivalence point? It's the first one. It's the first question, equivalence point. Question doesn't ask us that, but for us, it's a helpful number because we can think about it in terms of how many mils of base do I have to add, all right? So the equivalence point, well, we know because this is a one-to-one neutralization that if we started with 50 mils of acid, we know that for every 1,000 mils of acid, that's equivalent to 0.120 moles of acid, Chem1. And this is 1 mole of acid, it's equivalent to 1 mole of base. Again, it's a one-to-one stoichiometry. And I'm doing this the long way. And then therefore, for every 1 mole of, for every 0.240 moles of base, that's equivalent to 1,000 mils of base, and out comes 25 mils. So that's our equivalence point. After of base, it would take 25 mils of base to completely use up 50 mils of acid. The concentration is twice as much. I mean, we could have eyeballed this, but I wanted to work it out because it doesn't matter. All right, so we now know our equivalence point is 25 mils added base. Okay. So, depending on where we're at, we can figure out this in terms of mils of added base. All right, so if you think about this, again, our titration curve, that's 25 mils. There would be 10 mils. We know it's going to be close to our pKa, and so we can use this approximation. So the question is asking us, after adding 10 mils of base, now again, there are multiple ways of doing this, but the trick is to remember that all of the added base consumes some of the acid. And so we can then think of it again as fractions towards the end point. The end point was 25, all right, and so we can think of it in terms of amount of base and amount of acid. If so, we had, even though it says 50 mils, we think of it in terms of the amount of added base. It takes 25 mils of added base, and so whatever is consumed, in this case, the 10 mils that is consumed by the acid. So this is 10 mils of the external base, sodium hydroxide. That 10 mils of base becomes 10 mils of conjugate base. Again, the reaction, HOAC plus H3O. Whatever you add, whatever neutralized, gets shifted over to this side of the equivalence point, this side of the equilibrium. And so there are a total of 25 mils that you have to add, And so you add 1 mil, it becomes conjugate base. You add another mil, it becomes conjugate base. After 10 mils, it's effectively the same as their 10 mils of the conjugate base, leaving us with our original 25 minus that 10, 15 mils of unreacted. Again, this is a conceptual idea. You can convert it all to moles if you like, and the process would be exactly the same. But this is a time saver. We can think of it in terms of equivalents. How many equivalents have we added? To add one equivalent of base, we would have to add 25 mils. Right? And so to add a half equivalent, right? To add a third of an equivalent in this case. Right? So there are 15 mils of acid, in this case the conjugate acid, left. And so then we can plug that into our pKa plus the log 10 over 15 to give us the answer. Right? Now, I'm going to work it out a longer way on the slides, and you'll see that the answer is exactly the same. Right? So that's an alternate way of handling titrations. Rather than thinking about them in terms of moles, you can think of them in terms of mils towards the end point. Now, if this had been a diprotic acid, it wouldn't be any different. We would do one equivalent, and then we'd do a second equivalent. All right, and so whatever that one equivalent was, fractions towards that equivalent, we could talk about that one's buffer region and the like. All right, so there you go.